In this section, let's talk about functions. What do they represent and how can we use them in our course? Particularly when we come to chapter 3 with the limits, we're definitely going to see them again. We're going to see them again throughout the course. So what is a function? A function is a relation such that each x corresponds to exactly one or unique y. Sometimes I think of it as 1x having one right answer as we're used to. It's not a very good definition, but it's a good basis to start with. So let's take a look at a couple of possible functions, and let's take a look at these two relations actually, the first two cases, and are they a function or not? Let's try to determine that. So let's take a look at the first one. Now note how 4 corresponds to 6, but 12 corresponds to 6 and 14. So notice, does this violate the definition of the function? Well, the answer would be yes, because you have one x corresponding to two different y values. So yes, that definitely it's not a function according to our definition. Now let's take a look at number 2. Here we have a couple of x's corresponding to the same y value, but note that's actually okay, because the definition is actually not violated, because each x, for example 5, corresponds to one y value. Same thing with a 6. So number 2 is a function, whereas number 1 was not. Now let's take a look. We're going to spend for the majority of the video working with function notation. For example, let's start with an easier example. F of x equals to 3x squared minus 4x plus 1. We're going to have to find the following: f of 4, f of negative 1/2, f of a, f of 2 over m, and find x such that f of x is equal to 1. So I'll quickly go through the first example, and we'll spend some more time on the following examples. The first couple are fairly self-explanatory. F of 4, we basically plug it back into the original function, and we get negative 1 as the answer. With negative 1/2, we do the same thing, and let's work with fractions a little bit. So 3 times negative 1/2 squared, we're going to get 3 times 1/4, which is going to give us 3/4. Minus 4 times negative 1/2, well, we actually get positive 2 here, and then plus 1. So we're going to get 3/4 plus 3, which is actually 3 over 4 plus 12 over 4, which is going to give us 15 over 4. With f of a, because it's a variable, we're actually going to get an expression when we plug it in. We're going to get 3a squared minus 4a plus 1. For 2 over m, it's similar idea. We'll plug it in. So we're going to get 3 times 4 over m squared minus 8 over m. That's negative 4 times 2. And then plus 1. So we're going to get 12 over m squared minus 8 over m plus 1. Now, if we're trying to find x such that y value is given, that's the opposite situation. We're going to have the equation 3x squared minus 4x plus 1 equals to 1. And then we have to solve for x. If you recall, with quadratic functions, you want to set them equal to 0. So we can subtract 1 from both sides. So we're going to have 3x squared minus 4x is equal to 0. Note how we can pull out an x. So it's going to be x times 3x minus 4 is equal to 0. So we're going to get two x values. X equals 0 and x equals 4/3 are the answers. Now the next one is an example of a piecewise function. This is something, again, we're going to work with more in the following chapters. And note how it has two pieces. This rational function, 2x plus 1 over x minus 4, if x does not equal to 4, and 7 if x is actually equal to 4. And let's see if we can do the same thing. It's a little bit more challenging, but let's see if we can find these five portions or parts. F of 4, let's think about this one. I have it written as 7. Well, let's go back to our original definition. If x is 4, then the y is 7. So the answer would be 7. Now let's see about f of equals to negative 1/2. Well, negative 1/2 is not 4, so note how we have to plug it in to the top portion. So I have 2 times negative 1/2, which makes it the negative 1, plus 1. And then we have negative 1 over 4 plus 1 in the bottom. Actually, it should be negative 1/2, I believe. Yeah. So note how we work this out. So we're going to get I believe this should be negative 1 over 2. I think this should be a minor typo. But what we get on the top is 0 divided by negative 9 over 2. Yeah, let me actually fix this real quick. I think this is a 2 and then plus 1. So regardless of the denominator, we're going to get 0. Okay. With a, because a is a variable, we actually have no way of knowing if it's 4 or not, so we do have to follow the same setup as the original function. So it would be 2a plus 1 over a minus 4 if a does not equal to 4, and 7 if a does equal to 4. Okay, with 2 over m, it's a little bit more challenging because we have to specify if 2 over m is equal to 4 or not. But usually we specify what the variable equals to as opposed to the expression. So we have to do a little bit of work here. Let's set 2 over m equals to 4 to figure out what would be the condition on m that we're going to need. So note how we can multiply both sides by m. So it's going to be 2 equals 4m, which makes m equals to 2 over 4, which is a half. So the whole condition depends if m is equal to a half. Let's proceed. So if m is equal to 1/2, then the y would be 7. If m does not equal to a half, then you can plug in 2 over m into the first portion. And notice how I simplified it by multiplying both top and the bottom by m. And so we're going to get the simplified version. You can distribute it. And I think there's another minor typo here. I will fix and put the updated version. So I think you multiplied by 2. So this should actually be 4 plus m over 2 minus 4m. But it's similar kind of idea. So the actual definition, you have the top part. This should be 4 plus m. And the bottom part is 7 if m equals to 1/2. And trying to find x if the y is 1. Well, since the y is not 7, then we can set the top part from the original function equals to 1. We can multiply both top and both sides by the denominator, x minus 4. That's how come I get 2x plus 1 equals to x minus 4. And then we can solve for x like a regular equation. And I get x equals negative 5. So here we get only one answer. For the rest, we're actually going to focus on the idea called the difference quotient, which we're going to really need. This basically, the idea is the derivative. This is how we're going to define the derivative, or the rate of change, using the difference quotient. So we'll see it. Here's the first one. Let's start with the quadratic one, which is a little bit simpler, a little bit. So let's say if it's 2x squared minus 4x minus 5, what do we want to find? We want to find the following, f of x plus h. So we're going to build up to the difference quotient by taking different portions. Note how we do need a little bit of algebra. So x plus h is basically going to go instead of the x into the equation. So we're going to have 2 times x plus h squared minus 4 times x plus h minus 5. And note how I'm expanding x plus h squared, or there is a shortcut you can follow. Basically, it's the first term squared, x squared, plus twice of their product, 2xh, plus the last term squared, which is h squared. Then we can distribute the 4 minus 4x minus 4h minus 5. So note how we're going to get 6 terms in the final answer. Then what we want to do is find f of x plus h minus f of x. Subtract the original function, so quite a few terms would actually cancel. In fact, everything that doesn't have an h in it will cancel if we're doing this right. So notice how I rewrite the original part and then I subtract the function, which you can distribute the negative sign. That's how come the 2x squared will cancel, and also negative 4x, and also the negative 5, which I added right here. So we're going to end up with the 3 terms now, 4xh plus 2h squared minus 4h. And last, we want to do something that is actually a difference quotient, which is f of x plus h minus f of x over h. We're going to see this again coming up very soon with the derivative. In fact, we're going to attach the limit in front of it. And it helps to break these problems down. But definitely pay attention to these because we will see them again. How do we do this? Well, we've done the hard part. Notice how the top part is what we did in part B. And so I'm going to copy it right here, 4xh plus 2h squared minus 4h. And we basically divided by h, which the easiest way is probably to factor h out and cancel the top and the bottom. So we end up with 4x plus 2h minus 4. And what we've done is essentially derivative, except the h will go 0. So the h portion will go away. And we'll see how that plays out in the next chapter. And I wanted to try this with a rational function, which kind of works very similarly, but kind of the same idea. 5 over x is the one I wanted to try. So same idea. Let's do f of x plus h. This is the easy one. Basically, it's going to be 5 over x plus h in denominator. Then the next one is a little bit more work. So you want to do f of x plus h minus the original. So I have it as 5 over x plus h minus 5 over x. But notice these two I added. Basically, the first one I multiplied by x. The second one I multiplied by x plus h. And bring it to common denominator. So we're going to have x times x plus h in denominator. But on the top, we're going to have 5x. And then I distributed negative 5. So minus 5x minus 5h. Notice the x part cancel out once again. So I end up with negative 5h. So I took the negative out. So it'll be 5h over x times x plus h. So just a little work there. And then dividing it by h, it's going to be easier now. Let's see how that plays out on the next page. So it was basically, I took it as a fraction. The top part is what we had in B divided by h. So what I did is I kept the top fraction, negative 5h over x times x plus h times 1 over h. You can flip the bottom one. And notice how I cancel h's out. So we end up with negative 5 over x times x plus h. And that's it for this section.